Okay, so last time, what did we do? We talked about group representations. We proved Maschke's theorem, which states that every representation of a finite group is completely reducible. So what does that mean? That means that it can be written as a direct sum of irreducible representations. And so that allows us to reduce the classification of all representations of finite groups to the study of just the irreducible ones, because we can always break down a representation into just sums of irreducibles. So to do so, what we're going to do is we're going to introduce the theory of characters, which was introduced by Frobenius and Schur. This is their character theory. And we won't define a character today. We'll build up what we need to get to that point, and then next week we'll do the entire theory of characters. But the idea is to take a representation phi and it may be any degree like, and somehow we want to encode this in a complex valued function. So take this and encode it in some complex valued function that depends on the representation and goes from the group to complex numbers. And this thing will be called a character. And it turns out that the character will be given by just the trace operation. And so this whole chapter, we're going to think about representations in terms of matrices rather than the more abstract view of linear maps. Okay, so first things first, let me give you a definition. So let me define phi just once, so I don't have to keep writing the whole map. Let phi from G to G, L of V, and rho from G to GL, W be representations so all of today, phi and rho will be representations, both of the group G, which will be finite, and phi will be acting on the vector space V, while rho will be acting on the vector space W. Okay, a morphism, this terminology comes from category theory, but you might also see it written as intertwining map. From the representation phi to the representation rho is a linear map, let's call it T, between the vector spaces associated to the representation, such that T phi G is equal to rho G T. So in other words, applying this, applying the action of G to a vector through the representation phi, and then mapping to W is the same as first mapping to W and then applying the action of G using the representation rho G. Okay, so in a diagram, what this looks like is the following. We have phi G here. We have rho G down here, T, T, and this diagram commutes, so you can go either direction here, and the equality holds. So note how if T is a bijection, then this definition here is the same as an equivalence, which I defined last time, an equivalence of representations. So T is to representations as a homomorphism is to a group. So morphisms are to representations as homomorphisms are to groups. Right? So for this reason, we're going to write hom g phi rho for the set of all morphisms from phi to rho. Okay, so in the literature, you might also see this written as hom g vw. There is an abusive notation that happens a lot in the literature where the vector space is referred to as the representation, which sounds a little weird at first, but the representation, the actual map itself in that case would be the implicit thing. I prefer this perspective, but I'm sure at some point we'll probably switch to the other one. I can't remember if Steinberg does or not, but I would guess that he does. Anyway, so notice that however you define this thing, this is a subset of the set of linear maps from V to W. Right? It's just a set of linear maps from V to W that have this certain property. What property? This one here. Okay, so here's a remark. Observe that T from V to V belongs to hom G of phi phi if and only if T phi G is phi G T for all G and G. So that's just the definition. And what does that mean? That means that T commutes with all elements of the image of phi. So this is the same as saying T commutes. Another way of saying that is T centralizes. Commutes with or centralizes the image of phi. Okay, so that's a strong condition. Note that there is always one map that does this, which is the identity map. So this guy is always in hom G. All right, so let's start ourselves off with a proposition. Let T be in the hom set phi rho. Then the kernel of T is a G invariant subspace of V, and the image of V is a G invariant subspace of W. So, I mean, the proof is very simple. So you let V be an element of the kernel and G be in G. What do we want to do? Well, we want to show that if we apply phi G to V, well, then it's still in the kernel of T. Right? How do we test that? We apply T to phi g v. But if T is in the Hom set, then this is equivalent to, that should be a rho. It should be a rho g. That's equivalent to rho g T v, but v is in the kernel, and so this is rho g 0, which is, of course, 0. And so that implies that v is in the kernel, phi g v is in the kernel of T, and so the kernel of T is G invariant. And for the image, let W be in the image. Let's say that W is equal to T of V for some V and V. Then I want to show that rho G W is also in the image of V under T. Well, rho G W is rho G TV, and this is the same since T is in the Hom set as T phi G acting on V. And this is in the image of V under T. Okay, so then that implies that the image of V under T is G invariant. And that completes the proof. So here is another statement that's true. It's not hard to prove, so I won't to save some time. But this is in fact a subspace, not just a subset, but a subspace of the set of linear maps from V to W, which itself is a vector space. Okay, so you just gotta check a couple axioms there. All right, so the next lemma is going to be one of the most important results in representation theory, and is essentially an observation due to Schur that morphisms between irreducible representations are kind of limited in a sense. So this is called Schur's lemma. That's what it's referred to as in the literature. So as usual, we let phi rho be, well, in this case, we're going to let them be irreducible representations. Of a group G, and we're going to let T be in the Hom set. So that's all morphisms between phi and rho. Then Schur's lemma says that either T is invertible or T is 0. And if T is invertible, since it's already in this Hom set here, that's the same as saying that T is an equivalence of representations. So if phi and rho are irreducible representations, and I find a morphism between them, well, then that morphism is either an equivalence or it's 0. There are no other choices. So consequently, two things follow from this. One is that if phi is not equivalent to rho, this is not equivalent, then the Hom set, so the set of all morphisms from phi to rho, is equal to 0. And the second consequence is that if phi is equal to rho, then t is equal to lambda I for some lambda constant. I here is the identity map. Okay, so again, this is an extremely important lemma. It comes up in several cases to prove lots of important results. So it's worth proving this. So let's start with the first statement up here. If t equals 0, then we're done. So let's assume otherwise. So assume t is not 0. Since we already showed that the kernel of t is G invariant, and phi is irreducible. So remember what irreducible means? It means that the only G invariant subspaces of V are going to be 0 and the entire space V. So the fact that the kernel of T is a G invariant subspace tells us that the kernel of T is the 0 set or the entirety of V. But we're assuming remember, that T is not 0. And so that implies that the kernel of T cannot be the 0 set. And so that implies that the kernel of T must be equal to V. So, wait a minute. I have this backwards, don't I? Yes, I do. Okay, so T is not 0. Yes, okay, so if T was 0, then the kernel would be all of V, right? So T is not 0 implies that kernel of T is not V. Sorry about that. And so this is 0, and so that implies that T is injective. Yes. Okay, I should fix my notes. Okay, so we want to show that this map T is invertible. So the other thing we have to show is that it's surjective, right? And well, the other thing we showed earlier is that the image of T is also G invariant, and that since we're assuming that rho is irreducible, well, that means that the only invariant subspaces of W are going to be 0 and all of W. And so that implies that T of V is either 0 or W. Okay, so if T of V, so if the image is 0, well, that just means that T is 0. So that can't be the case because we're assuming T is not 0. And so that implies that T of V is equal to all of W, and so T is surjective. We have injectivity, we have surjectivity, that implies invertibility, and so the first statement has been proven. Okay, what about the consequences? Well, A is almost immediate, right? So if phi is not equivalent to rho, well then T must be equal to 0 for any T in the Hom set. And so this implies that the Hom set is just 0. Okay. And for B is just ever so slightly trickier. Steinberg gives a different proof of B in the book. This is the one that I like. So just let L be a constant, which is an eigenvalue of T. So this is the first place where we're really using the fact that we're considering all vector spaces to be vector spaces over C. So the fact that this operator has an eigenvalue depends on this fact. Right? If lambda were just an R, then it may not necessarily be true. But since the eigenvalues of T are given by the characteristic polynomial, and all polynomials have complex roots, then an eigenvalue does in fact exist. Okay, so that's our fundamental theorem of algebra. Okay, so let E lambda be the corresponding eigenspace. So this is the space of all eigenvectors associated to the eigenvalue lambda. And what I want to show very quickly is that this eigenspace is actually G invariant. So for every V in E lambda and G in G, we have the following. We have that T phi G V. Well, T is in the Hom set, and so this is phi G T V. So remember, phi is equal to rho in this situation. But V is an eigenvector of T with eigenvalue lambda. Right? We're assuming that V is in the eigenspace. So this is phi G lambda V. Phi G is linear, so I can pull out this lambda. And now I have that T phi GV is lambda phi GV. And so that implies that phi GV is in the eigenspace. And so the eigenspace is G invariant. Okay, well, once again, what I'm going to use is the fact that my representation is assumed to be irreducible. That means that the only G invariant subspaces are 0 and V itself. And so this E lambda is either 0 or all of V. If E lambda were 0, well, then that would imply that T is equal to 0. So this case implies that T is equal to 0. And we're already assuming that T is not 0, so that can't be the case. So then E lambda is equal to V. But how does T act on E lambda? So on E lambda, T is just lambda times I, right? So how does T act on an eigenvector? It just multiplies it by lambda. Okay? But E lambda is equal to V, and so T is equal to lambda I on all of V. Okay, and so that proves part B. And we're done. So this is Schur's lemma. It's extremely important. We're going to see it come up, I think, before the end of this session. Well, actually, we'll see it come up many times. In fact, I think I'm about to give a corollary of Schur's lemma, which is incredibly strong. Yeah. So it turns out that this is just enough to give us the classification of irreducible representations of abelian groups. So here's a corollary. Let G be an abelian group. So that is a group for which the binary operation commutes. Then any irreducible representation of G has degree 1. Okay, here's the proof. So let phi be such a representation. So phi from G to GL of V. So this is an irreducible representation of the abelian group G. And let's fix any H in G. Also, let's set T equal to phi H. Well, then for all G in our abelian group, we have that T phi G is equal to phi H phi G is equal to phi HG because phi itself is a homomorphism. But since G is abelian, we can commute these two. So that's phi GH. Oh, I dropped my T somewhere. Let's see. Oh, no, I didn't. No, I didn't. We're good. Phi GH. And so that's phi G, phi H. But phi H is equal to T. So we just showed that this map T, which is just phi H, is a morphism of representations. Well, a morphism of phi with itself. Okay, anyway, since phi is irreducible, that allows us to apply Schur's lemma. So by Schur's lemma, that tells us that phi h, or t equals phi h, is an equivalence. Because it sure isn't 0. Okay. And from part B of Schur's lemma, we get something even better. We get that phi h is equal to lambda hi for some lambda h constant. So the h subscript here is just indicating the dependence on h here. Okay, then for any v not equal to 0, and v and any k constant, phi h of kv is equal to lambda hi kv, which is equal to lambda hkv, and this is in the span of the vector v. So remember, the span is all the linear combinations of the vectors in the set. There's only one here, so the span of v is just all scalar multiples of v. So this implies that the span of v is G invariant, since h was arbitrary. Okay. So then, oops. So then we use this irreducibility condition again on phi to tell us that since span of v is G invariant, then it's either 0 or all of v, and well, it can't be 0, and so it must be all of v. Okay, Great. So that proves that result. So that just about classifies all the representations of or irreducible representations of an abelian group. We know that they're all degree 1. Okay. So here is a nice corollary of that from that pertains to linear algebra. So again, let G be a finite abelian group. And let's let phi, we're going to think of phi now as a representation where the image is a matrix. So we can always swap between this view of linear maps and the view of matrices. Well, then there is an invertible matrix T such that T inverse phi G T is diagonal for all G in our group. That's a terrible G. Okay. So if I give you a finite abelian group and a representation in terms of matrices, then we can always find an invertible matrix T such that the conjugation of phi G by T is diagonal just for any G. So by Maschke's theorem, that's the one the big one we proved last time. Phi is completely reducible. So the only assumption you need here is that G is a finite group, and this follows. Okay, so we have that phi is equivalent to a direct sum of representations, each of which is irreducible. Now, since G is abelian, we know that the degree of each phi I has to be equal to 1. So that was the last proposition. Okay, and hence n is equal to m. Is the degree of the total representation must be equal to the sum of the degrees of the individual representations. And if the degrees of each of these is 1, well, then m better be equal to n. Okay, then as a matrix, what we have, so we have this whether or not these representations are degree 1. So maybe I should have written it earlier, but the matrix representation of T inverse phi G T is just phi G 1 through phi G n on the diagonal with zeros elsewhere. And since these things are all degree 1, these are really just scalars. So these are elements of C star. And so this thing's diagonal. That's it. And so that implies T inverse phi G T is diagonal. Okay. Oh, sorry, I didn't say what T was. So T is this map that gives the equivalence between phi and the direct sum here. Such a thing exists because we know these things are equivalent. Okay, and so that completes the proof. So Steinberg gives another nice corollary for linear algebra. It's just an example of something you can get from that proposition. So I'm not going to prove this one, but I will just write it down really quickly in case anybody hasn't had the chance to read the section. So if you have an m by m matrix of finite order, so that just means that a to the n is equal to I for some n, then A is diagonalizable. And moreover, the eigenvalues of A are the nth roots of unity. Okay, so the proof is in Steinberg. I'm going to pass this one up since it's just an application, and I'm more worried about getting through the theory right now. We'll do plenty of application later. From now on, just to get all the notation on the table, G is going to be a finite group. Phi and G, I already defined those as representations. And we're going to write phi G as a matrix. And so the components, sorry, that should be phi ij. The components will be functions of G with their image in the complex numbers. So phi G is a linear map, and we can represent it by a matrix. And the components of that matrix are going to be these phi ij functions, which depend on G. Okay, here's a definition. So with G a finite group, we can define L of G, sometimes written as C with a G in the superscript. We may have already defined this as the set of functions f from G to the complex numbers. Okay. Then L of G is an inner product space. Yes, we did indeed prove this. We proved this in the linear algebra lecture, which I think was the third one. With inner product given by, so if I have F1 and F2, then their inner product is 1 over the magnitude of G times the sum over G and G of F1 of G, F2 of G, complex conjugate. And this L of G, for reasons that will be clarified maybe later, this thing is called the group algebra. So if you are like me, you have seen the group algebra written differently. I always thought of the group algebra as a linear combination of the group elements. And so the group elements were the basis vectors. The perspective here is a little different, but I think equivalent. So it might be useful to switch back and forth between the two constructions, but I think for this chapter, we're just going to view it this way. Okay. So our next big goal before we end the session is going to be to prove what's called Schur's orthogonality relations. So let me just write it down so you know what we're working towards. We're working towards the following theorem. So suppose phi is not just a representation, but it's a unitary representation. So that means the so phi g is unitary for all g, right? And so is rho, but maybe it's of a different degree. And let's assume that these are inequivalent. So there's no equivalence between them, and they're irreducible. And from the notation, you could gather that they're unitary representations. Well, then the following hold. The inner product of phi ij with rho kl. So these are elements of the group algebra, right? They're maps from the group to the complex numbers. Well, first of all, this thing is equal to 0. And secondly, the inner product of phi ij with, that should be a phi, with phi kl is equal to 1 over n if I is equal to k and j is equal to l, and it's equal to 0 otherwise. So these are called Schur's orthogonality relations. Okay, so we're working towards this, and we're going to need several intermediate results, one of which is the following proposition, which is going to go ahead and make use of that Weyl unitary trick again. So let phi and rho be representations as usual, and let T be a linear map from V to W. Then the following hold. The map called T sharp, which is defined by Weyl's unitary trick here. This is just, Steinberg calls this an averaging trick, which is really a good name for it, I think. Well, this is in the Hom set between phi and rho. So if I give you some linear map between V and W, then you can construct a morphism between phi and rho given that linear map by doing this averaging over the representations. Sorry, over the group, but using the representations. So we also have that if T is in the Hom set between phi and rho, then T sharp is equal to T. So if T is already in the Hom set, then doing this averaging trick won't do anything. It'll just make T sharp equal to T. Yes, looks very similar to the twirling map in quantum mechanics because it is. So C, the map P from VW to G phi rho defined by P of T equals T sharp is a surjective linear map. Okay, so for your quantum perspective, if you take the twirl of a map which is already a morphism or an intertwining map of representations, well, then you just get the same map again. If you the twirl map itself, so this sharp symbol, if you like, is itself a surjective map from. I was writing this a different way before. This is the same as the linear map between V and W. Well, it itself is a surjective linear map from the space of linear maps from V to W to the space of G invariant maps, or sorry, morphisms of phi and rho. Okay, so I believe I want to prove this. Yes. Okay. So for A, we want to show that this twirl, or T sharp, is a morphism when T itself does not have to be. So T sharp applied to phi H, we want to show that that's equal to phi H applied to, phi H T sharp. So this thing is equal to 1 over order of G, sum over G and G of rho G inverse T phi G phi H, which is 1 over the order of G, sum over G and G. And we're just going to use this homomorphism property here that all representations satisfy by definition. Okay, now we do this trick again where we remember that as G ranges over the entire group G, so does G times H, right? The action of H on the group G is surjective. I think another name is transitive. So what we're free to do is apply a change of variables. So maybe a more clear way to explain this is as follows. This is the same thing as the sum over GH and G of rho, and now this is going to be what will that be? Well, we're going to keep this G inverse for now, phi GH. So doing this sum is the same as doing this sum. You're still obtaining every element in the group. And since addition is commutative, these mean the same thing. Okay, and now we can do a little substitution. We can call this GH thing X. And so what's G inverse in this case? We can, so X is GH. And so we can move G to the other side. And so this is equal to HX inverse. And so this is rho HX inverse. Make sure I have that right. Yes. T, and this is X. And now we can use that homomorphism property again, because rho is a representation. And so this is the sum over X and G of rho H, rho X inverse, T phi X. And we're pretty much home free from here. We move the rho H outside, and then what's left is rho H, and this whole thing is just the twirl or T sharp, if you like. And that's it. So that proves A. Now for B, if T is in the Hom space, what we want to show is that T sharp is just equal to T. Well, T sharp or the twirl, is equal to 1 over the order of G, sum over G and G of rho G inverse T phi G, 1 over the order of G, sum over G and G. And we're going to use this fact that T is in the Hom space to move the phi to the other side, but when we do that, it becomes a rho G. This is rho G inverse, rho G T. And now rho G inverse, rho G, well, we use the homomorphism property again. I'll add that step in here, why not? This is rho G inverse G times T. G inverse G is the identity. Rho maps the identity to the identity. And so this is just 1 over the order of G, sum over G and G of T. There's no more G dependence here, so this is just T order of G times. And so we're left with T. Okay, so that proves B. Now C is to prove that this sharp map is, or the twirl is a surjective map from the set of linear maps between V and W and the subset, which is morphism. Okay, so for C, well, we have to prove a couple things. So for linearity, which is one of the assertions, P of a constant times a map plus another constant times another map is equal to, by definition, the twirl of those maps, which is equal to 1 over the order of G, sum over G and G of rho G inverse C1 T1 plus C2 T2 phi G. And that's equal to, well, let's just go with it. Let's distribute everything. Rho G inverse T1 phi G plus C2 1 over order of G, rho G inverse T2 phi G, and this is equal to C1 T1 sharp plus C2 T2 sharp, which is C1 P of T1 plus C2 P of T2. Okay, so that establishes the linearity of P, which is the twirl or this sharp map, however way you want to call it. So for surjectivity, if T is in the Hom set, then B, part B, implies that T is equal to T sharp, which is equal to P of T. And so P is surjective. I took an arbitrary element of the Hom set and I wrote it as the image of something in the space of linear maps, which is just T itself. And so that is the end of the proof. Okay. So for you people in quantum information theory, you have probably seen or used maybe a different variant of Schur's lemma. So I would like to prove that one as well. And it's very useful. We will use it here. Let phi rho be irreducible representations of G, and let T map from V to W. we want it to be a linear map, then if phi is not equivalent to rho, then the twirl of t is equal to 0. And if phi is equivalent to rho, I shouldn't say equivalent, if phi is equal to rho, then the twirl of t, or t sharp, is the trace of t over the degree of phi. Remember, the degree of phi is the dimension of the vector space that the representation acts on. Okay, proof. For A, if phi is not equivalent to rho, then by Schur's lemma, the Hom space is equal to 0. We're free to use Schur's lemma because we already proved it. We're not cheating. Okay, so that implies, of course, that t sharp is equal to 0 because we proved that proposition which said that t sharp was in fact a morphism between phi and rho. Okay, maybe I should put curly braces around here. For part B, assume that phi is equal to rho. So by Schur's lemma, we have that t sharp, which again is in the Hom space, it's a morphism, is equal to lambda times I for some lambda in C. So this comes from part B of Schur's lemma as we previously proved it. Now what we want to do is we want to get a little more specific and actually solve for lambda. Well, the trace of t sharp, or the twirl, is the trace of lambda I, right, because it's just equal to lambda I. And the trace is linear. We can pull out this constant. And the trace of the identity map is the degree of representation, because it's the dimension of V, which is the same thing. This is lambda times the dimension of V, which is the degree of phi. On the other hand, the trace of t sharp, or the trace of the twirl, is, well, we can write out the twirl explicitly and then use linearity. And what we get is 1 over the order of g times the sum of the trace of phi g inverse t phi g. Okay, so this sum and this 1 over order of g and this stuff in here all together makes the twirl, and I just use the linearity property. Okay, and now the trace satisfies this nice property where we're able to cycle the individual pieces inside of the trace. Right? So the trace of ABC is the same thing as the trace of CAB. Right? And so this is 1 over the order of g, sum over g and g of the trace of phi g inverse t. And you can probably see where this is going now. So phi g inverse, that's just the identity. And so this is the trace of t. So this is 1 over the order of g, sum over g and g of the trace of t. And this is just going to be the trace of t. This has no dependence on g. So this is just order of g copies of the trace of t. And so the orders of g cancel. So let's combine these two. We have that this and this are equal because they both come from the trace of t sharp. And so that implies that lambda is equal to the trace of t over the degree of phi. And so phi itself, sorry, not phi, t sharp is equal to lambda I, which is the trace of t over the degree of phi times the identity. So that is where this constant comes from when you use that in quantum information theory. Okay. So it turns out that when phi and rho are unitary representations, the matrix for P, for the twirl, so this is the twirl operation itself, not the twirled map, the twirled operation, so this sharp thing, it has a special form. So first recall, just a tiny bit of linear algebra. Recall that the matrices, I'm going to write them as Eij with a superscript. The reason I put the superscript here is because I don't want to put it in the subscript and have you confuse this as components of a matrix. This thing is a matrix itself. Right? So the components will be listed as Eij KL for the KL components. Okay, so these matrices with a 1 in the Ij component and a 0 otherwise, they form a basis for the set of, or the vector space of matrices that are m by n. So in other words, we can write any matrix as the sum over I and j of the components of the matrix times the basis matrices Eij. So this notation brings us back to the Einstein summation convention, which I will now violate. I apologize if there are any GR people here. So let A be an R by M matrix, and let B be an N by S matrix, and let EKI be an M by N matrix. Then the following equality holds. A times EKI times B, the LJ component of the resulting matrix, is equal to A LK B IJ. So it's really just a straightforward computation, but in case anybody can't see it, this A E K I B L J, so by the definition of matrix multiplication, this is just the sum over x and y of A L X E K I X Y B Y J. And now all terms are going to be 0 except for when x is equal to k and y is equal to I, right? Because every other entry of this matrix, EKI, is 0. And so this is equal to A, L, K, B, I, J. So again, just a straightforward computation, but the indices flying around everywhere can be a little tricky. So figured I'd write it out. Okay, and we're only going to need this lemma to prove the next lemma, which is the one we actually need. So let phi be a unitary representation, and same for rho, possibly of a different order. Sorry, different degree. So let these be unitary reps. We're not assuming irreducibility here. Let's let A be one of these basis matrices, which sits inside of Mn of C, which is the space of all matrices, complex matrices that are M by N. Well then, A Lj, so the Lj component of A sharp, so the twirl of that is equal to the inner product of phi ij with rho kl. Okay. So maybe I want to be able to see this, so let's just move this up. Okay, so since rho is unitary, what does that mean? That means that rho g is unitary for all g. That means that rho g inverse, which is the same as rho g inverted, is just equal to the adjoint of rho g. So remember, I'm using the star notation or the dagger notation. They mean the same thing, whichever you like better. Thus, rho Lk of G inverse is equal to rho KL of G bar. So this is just saying that the adjoint in the matrix form is just giving us the conjugate transpose. Now compute ALJ sharp, so the twirl of this ALJ guy. Is that what I want to say? Rather, I want to say the LJ component of A sharp. Yes. Okay. So this is 1 over the order of G of the sum over G and G of rho G inverse EKI. That should be a phi G LJ. And now we use lemma 1 here. This is equal to 1 over the order of G of the sum over G and G of rho LK of G inverse phi ij of G. That's exactly what the first lemma tells us. And this is equal to 1 over the order of G of the sum over G and G of rho KL of G complex conjugate phi ij of G, which is just the definition of the inner product between phi ij and rho KL. And that completes the proof. Okay. So if I have two unitary representations, then if I take the twirl of A, the LJ component is given by the inner product of the components of the representations. Okay. So finally, we make it to Schur's orthogonality relations. We can now prove them. And I'll give a couple of nice consequences of this immediately after, and then we'll end there. Okay, so let phi and rho, as usual, be representations, but not just representations. Let's let them be unitary. We want them to be the same degree here, but inequivalent. and irreducible. Well, then the following holds. The inner product of phi ij with rho kl is 0, and inner product of phi ij with phi kl is 1 over n if I is k, j is l, and 0 otherwise. Okay. I already wrote this out, but just so we can see it, here it is again. Okay. Here's the proof. Let's start with 1. Let A equal E ki, once again, which is an m by n matrix. Well, then A sharp, or the twirl of A, is equal to 0 by Schur's lemma, because it's definitely not an equivalence of representations. And those are the only two options. So on the other hand, ALJ, sorry, A sharp LJ, I should say, is equal to phi ij rho kl by lemma 2. Thus, putting these together, we have phi ij rho kl, inner product is equal to 0. So that proves the first part. Okay. What about the second part? All right, so let's have A equal to EKI again. And let's apply Schur's lemma one more time. So by Schur's lemma, the twirl of A must be equal to the trace of EKI over N times I. So this is Schur's lemma in that second, the variant that we proved earlier. By lemma 2, the LJ component of this map is equal to phi ij phi kl. So let's consider several cases. If j is not equal to l, well then the LJ component of the twirl of A, which is equal to phi ij phi kl, is equal to 0. This is since the identity is diagonal. If I is not equal to k, well then EKI has only zeros on the diagonal, and so the trace is 0. And that implies that 0 is equal to j sharp inner product phi ij with phi kl. Okay, and finally the case where L is equal to j and I is equal to k should be 1 over n. So finally, if L is equal to j and I is equal to k, then EKI has a single one, number 1, on the diagonal, and all other entries are 0. That implies that the trace of that matrix must be equal to 1. And so 1 over n is equal to ALJ Schur phi ij phi KL. And that completes the proof. So that gives us Schur's orthogonality relations, which are these two relations here. So if I have any two unitary representations that are irreducible, if they aren't equivalent to each other, well then their components are orthogonal in that group algebra. And the components of phi itself are also orthogonal unless unless I is equal to k and j is equal to l, in which case the inner product evaluates to 1 over n. Okay, so if you just renormalize this result, then you get the following corollary. So I won't prove it. I will just tell it to you. Let phi be a unitary map, or sorry, unitary irreducible representation of G. Let's say the degree is D. Then the D squared functions given by the set square root of D phi ij, where I and j are between 1 and D. This thing forms an orthonormal set. So orthogonality, remember, gives us linear independence. So we showed that in the linear algebra portion. And so in fact, we have the following. And this is the thing we're going to end on. Let G be a finite group. Let phi 1 through phi s be a complete set of representatives of the equivalence classes of irreducible representations. Okay. So you take all of the equivalence classes of irreducible representations. Each class has many different representations in it, right? That are all equivalent to one particular irreducible representation. And we're just selecting from each equivalence class one individual irrep. Well, oh, I need one more thing. And set the degree of phi I to be di. Well, then the functions of this form, where k runs between 1 and s, so this s, and ij again run between 1 and, well, this time dk. These form an orthonormal set in the group algebra, and hence S must be less than or equal to d1 squared sum through ds squared, and that must be less than or equal to the order of G. Okay, let me explain that last part. So each of the individual irreducible representations, well, their degree has to be at least 1, right? That's how we get this lower bound, right? If they're all 1, well, then this lower bound, well, then if they're all 1, then this is going to be S. Okay? That's the case when G is abelian, right? And I think that might be an if and only if statement, if I remember correctly. I think Steinberg does say that. So this inequality here is an equality if and only if G is abelian. I believe that's true. It'll turn out, well, first let me see how we get this inequality. So as I was saying before, orthogonality gives us linear independence. And so this thing is going to end up being a basis for the group algebra. But the group algebra, its basis is going to be, it's going to have the same order as the group. Right? So the dimension of the vector space, which is the group algebra, is equal to the order of this group. And so the sum here of these things must be less than or equal to the order of G as a result. And it's going to turn out that this is actually an equality. And so we'll see that I believe next time. But there you have it for now. Any questions?
Where does the square come from? Can you re-explain that?
Let's see. I believe it's this normalization factor here, the square root.
No, I mean where does the sum of the squares?
Okay, let
Do
me
we have some of the squares of the DI?
Yes,
Not,
yes, I see what you mean. Okay, so let's backtrack. We're getting this inequality from the fact that a basis for the group algebra will have order G, and these things are orthogonal, so their order must be uh, yes. How many of these things are there? Right, these phi ij's. Well, the representation is degree dk, right? Sorry, the representation is degree dk. And so how many components are there? There's
oh
dk
yeah.
squared. Yeah,
Okay,
yeah,
I see it. Yeah, okay. Okay. I see
yeah.
it. Thank
Sorry,
you.
it has nothing to do with this coefficient here.
Yeah. All right.
Just going.
Thank you.
Yeah, no
Thank you.
problem. Okay, any other questions? Okay, so let's go ahead and end there.